Welcome back to the Advanced Microcontroller series. In this session, we are learning about microcontroller interrupts. And here is the agenda: Introduction, Design, Circuit on board. An interrupt is a communication process setup in a microprocessor or microcontroller in which an internal or external device requests the MCU to stop the processing. The MCU acknowledges the request, attends to the request, goes back to processing where it was interrupted. Interrupt versus polling, loss of events, response, power management. Let's look about which having bad response, which having good response, inefficient power management and which having efficient power management and loss of events. So this is what pull down circuit. But on board we having pull up circuit. So this is the pull up circuit. Let's write the hardware response. So when we connect this RB0 to the CRO, you will get hardware response. So here this axis varies with time and this axis varies with voltage. So here it is 0 volt and here it is 5 volt. And this is what? 0. So when RB0 connects to the CRO and switch is open, what will happen when switch open? You will get the high signal, isn't it? So you will get the high signal like this. So this is the hardware response when switch is open. So when switch is closed, so how you will get the hardware response when switch is closed? So here switch is closed, you will get the hardware response like this. So this is voltage 5, 0, Hertz and this is T. So this is the hardware response when switch is closed. Okay, now I am going to write one code. Let's discuss about the software response. So this is the code. So here you can see initially code took 100 milliseconds to complete. So when switch is pressed, RB0 equals to 0 means switch is pressed, it took 1000 milliseconds. Okay, let's write the response. So here you can see this is the hardware response. So now I am going to write the response. So initially code took 100 milliseconds to complete. So here 0 volt, 5 volt, this axis varies with time and this axis varies with voltage, and this is 5 volt and this is 0 volt. So this is what? X. So here I am going to write X plus 100. So initially, so initially code took 100 milliseconds to complete. So this is the hardware response. So what will happen when switch is pressed? So when switch is pressed, you will get the response like this. So, and next it detects the switch press. Then code took 1000 milliseconds. See here, it detects switch press. It takes too much delay, right? Why it takes too much delay? Why? Because it is polling method. So what you observed? Bad response. One thing you observed, bad response. So when switch is pressed means RB0 equals to 0. It continuously checking, right? So due to this, what happens? Inefficient power management. And third one is event loss. So when switch is pressed, key press, after that you will release it. So here event loss happens. So how, I will explain later. So we having disadvantages, right? So 3 disadvantages. So how to overcome this? We use interrupt. So interrupt can be generated from external sources. So microcontroller having timer which generate interrupt. Switch is external peripheral which generate interrupt. Hardware peripheral generate interrupt which is called hardware interrupt. See here, this is the interrupt classification. Interrupt is classified by 2 types, hardware interrupt and software interrupt. So hardware peripheral generate interrupt which is called hardware interrupt, and few software instructions generate interrupt, so that is called software interrupt. So for example, INT, then trap, then exception, these are the interrupts. Under the hardware interrupt, we having 2 types, non-maskable and maskable. So non-maskable means I can't suppress or ignore this interrupt. Mask means something you can hide or ignore, isn't it? So maskable means if required I can suppress this interrupt or ignore this interrupt. Non-maskable, this interrupt critical areas are there, example power, so we need backup. And under the maskable we having 2 types of interrupt, external interrupt and internal interrupt. And next is the interrupt handling. So instruction executing one by one, isn't it? So while executing instruction, interrupt happens. So super loop. So here you can see this is the super loop, isn't it? While of 1. When interrupt occur, when it will occur? When instruction is incomplete, its execution is paused. Then control will go to the interrupt handler and task is resumed. So now let's discuss about the interrupt handler, that is IVT, interrupt vector table. So let's say we having 0, 1, 2, 3. So okay, I'm going to write this here. Yeah, so So 0th index have INT interrupt, and here 1 having timer 0. So it having addresses also. So let us consider one random address 1, 2, 3, 4, and here for timer 0 I am considering some random address like this. So it's having some random address, assume. So So here we having some code. So what will happen initially, I1 interrupt will execute. Then control will go to the timer 0 here. So here control will go to the address, this one 0x323455. So now what will happen, 0x2345. So that is what, timer 0 ISR. So what will happen here, once control will go, that ISR will executed. So once execution, then again what happen, task will resume, then again it will come back. So in case of IVT, addresses are stored in that tables. So we have separate ISR of each interrupt. So what is ISR? And before that, in case of IVT, doesn't matter how many interrupts are sourcing there. So for all interrupt sources, one ISR is there. So you are executing interrupt I1. We have interrupt because of timer 0. All the interrupt sources execution will done, task will resume. Whenever you are using PICSimLab Simulator, so it uses ISR interrupt. So if you are using 8051 microcontroller, then you go that uses IVT, means interrupt vector table. So here we are using PICSimLab Simulator, so let's focus on the ISR only. Okay, so what is ISR? Service routine. ISR means what? Interrupt service routine. It is similar to a subroutine, attends to the request of an interrupting source. So during execution, you got interrupt. Current execution paused. So here I interrupt. So I instruction occurred and completed. Next instruction is I plus 1. So PC means program counter having address of this interrupt instruction. So this address will be shifted to the stack pointer. The execution stopped. Control will go to the handler. So which is the handler? ISR. So ISR executed, task is resumed. When ISR execution done, task is paused. So PC is having address of the next instruction. When you coming back after execution ISR, how your controller will know which instruction it has to execute? So that address from PC is loads, right? So in the stack pointer. So microcontroller read that address from the stack pointer and it will pause the execution from that point. So here you can see ISR, similar to subroutine, attends to the request of an interrupting source, clears the interrupt flag, should save register contents that may be affected by the code in the ISR, must be terminated with the instruction RETFIE. So we have few register. So when you going into ISR, you are updating those register. So even in the ISR also, when you coming back, those register value are updated. If any register you are updating, you can take backup of those register. That is called contents of register. So RETFIE means what? Return from interrupt. So when interrupt occurs, the MCU completes the instruction being executed, disables global interrupt enable. Global interrupt enable means GIE. GIE, and places the address from the program counter on the stack. Return from interrupt. So what you should include and what not should include. So in ISR, keep simple and short, and blocking statement you need to avoid. Okay. And next is the interrupt latency. It is the time from interrupt occur to go to the ISR and execute the first instruction. For example, airbag system. So here instruction is accident. Execution of first instruction is very important. Okay, let's open the data sheet. So here we need to search PIC16F877A data sheet. So here you need to search the interrupt. Keep search. See, interrupt went, right? See, here interrupt is there. So here you can see PIC16F877A family has up to 15 sources of interrupt. So it has 15 sources of interrupt. So here you can see the interrupt control register records individual interrupt requests in flag bits. So doesn't matter which interrupt it will go to ISR. When it come back, how to differentiate which interrupt using flag bits. So whenever interrupt occur, it will set interrupt flag for all 15 interrupt. We have 15 different flag. So here you can see 15 different flag. So int con, so it having 7 bits. 7 bits. So here you can see it having 7 bits. GIE means Global Interrupt Enable. So here you can see Global Interrupt Enable bit enables all unmasked interrupts and disables all interrupt. Means when GIE equals to 1, set means what? That is equals to 1. It enables all interrupt. And when GIE equals to 0, 0 means what? Clear. It disables all interrupt. So that's all about the interrupt. In the next session, let's discuss about the INT interrupt. So latency is determined by instruction time, how much of the context must be saved, how much of the context must be restored, the effort to implement priority scheme, time spent executing protected code. That's all about the today's session. Let's discuss about the external interrupt in the next session. Thank you all.